Hi, welcome on Insane Curiosity. Today we are going to talk about the detection of a radio signal from the Venus Ionosphere. The detection was made possible thanks to NASA's Parker Solar Probe. We'll tell you later why this is an important discovery, but first, what do you know about Venus? Here are some quick, interesting facts. 1. A day on Venus is longer than a year on Earth. 2. With a mean temperature of 462 degrees Celsius, Venus is hotter than Mercury, despite being further away from the Sun. 3. Unlike the other planets in our solar system, Venus spins clockwise on its axis. 4. Venus is named after the Roman goddess of love and beauty due to its bright, shining appearance in the sky. Of the 5 planets known to ancient astronomers, it would have been the brightest. 5. A hypothetical inhabitant of Venus would be called Venusian and not Venerian. Detected radio signal from Venus. Okay, now that we know something more about Venus, we need to take a quick look at what an ionosphere is. In fact, if we want to understand the detection of the radio signal on Venus, we have to recall some basic information about the ionosphere. Talking about Earth's ionosphere, it is the belt of the Earth's atmosphere in which the radiations of the Sun, and to a much lesser extent the cosmic rays coming from space, cause the ionization of the component gases. Extending between 60 and 1,000 kilometers of altitude, and therefore partially belonging to both the mesosphere and the thermosphere, it can be further divided into layers highlighting the different electrical properties due to variations in composition and intensity of solar radiation received. The Earth's ionosphere, 1, is home to all the charged particles in Earth's atmosphere. The Sun cooks gases there until they lose an electron or two, which creates a sea of electrically charged particles. 2. It changes, sometimes unpredictably. Because it is formed when particles are ionized by the Sun's energy, the ionosphere changes from the Earth's day side to the night side. 3. Disturbances there can disrupt signals. The ionosphere also plays a role in our everyday communications and navigation systems. Radio and GPS signals travel through this layer of the atmosphere or rely on bouncing off the ionosphere to reach their destinations. In both cases, changes in the ionosphere's density and composition can disrupt these signals. 4. The ionosphere constantly glows. And the airglow isn't just a beautiful sight. It's a useful marker for what happens in the ionosphere. Each atmospheric gas has its own favored airglow color depending on the gas, altitude, region, and excitation process, so we can use airglow to study where these gases are and how they behave. This is about all we needed in order to understand what the Parker Solar Probe just discovered about the Venusian ionosphere. Let's start. During a close flyby of the planet Venus in July 2020, NASA's Parker Solar Probe detected something very odd as it dipped just 517 miles above the Venusian surface. Its probe instruments recorded a low-frequency radio signal. This meant Parker had just skimmed into the Venusian ionosphere. This was an exciting achievement because it was the first time an instrument was able to collect in situ measurements of Venus's upper atmosphere. The last time was about 3 decades ago. These are precious data that could definitely help us take away some doubts about the nature of our twin planet. Astronomer Lynn Collison from NASA said he was just so excited to have new data from Venus, and we share the same thought with him because Venus is a fascinating world to us here on Earth. In fact, it is so similar to our own planet in size, with a radius of 6,051.8 kilometers, just a little shorter than the Earth radius, and composition, it's a rocky planet. But despite that, Venus is so crucially different from Earth. It is toxic, and it is a hot hell world that's likely completely inhospitable to life as we know it. Scientists are trying to understand how the two planets could have developed into such different worlds. This is a wonder of deep interest to astrobiologists, too, who are searching for other habitable worlds out there in the universe. By the way, every time we add some new understanding about Venus, we are excited. This is because it is hard to explore the secrets of Venus. Missions to explore Venus have been relatively few because landers can't survive the planet's huge 864 degrees Fahrenheit surface, or 462 degrees Celsius. This is also one of the reasons why we have a lot of landing missions directed to Mars rather than to Venus. Also, the incredibly thick atmosphere of carbon dioxide and sulfuric acid rain clouds is dangerous for probe missions. This is what makes it hard to tell what is happening on the Venus surface. From all the missions sent to Venus, we want to recall the Pioneer mission, Pioneer Venus 1 orbiter. The Pioneer Venus orbiter carried a radar altimeter, which was used to make the first global map of the surface elevations. The orbiter's main antenna was used to produce moderate-resolution radar images of the equatorial region. Pioneer Venus 2 bus and landers. The Pioneer Venus bus carried and released 4 probes which measured the atmospheric composition, temperature, and pressure as they descended toward a hard landing on the surface. Anyway, for these reasons, Venus has not been a popular target for dedicated missions. Most of the information we have about Venus came in fact from missions that didn't set the study of Venus as a primary goal. This was exactly the case of the radio signal detected by Parker Solar Probe. Parker Solar Probe was not meant for Venus. So, how did they detect the radio signal? As Parker conducted its mission to study the Sun in close detail, it used Venus for gravity assist maneuvers, slingshotting around the planet to alter velocity and trajectory. It was during one of these gravity assist flybys that the probe's instruments recorded the radio signal from Venus. Sometimes when we hear about radio signals from other planets, we think about the possibility of the existence of a form of life that is trying to communicate with us. So, was it a communication radio signal? Well, it seems not. Why? Before finding out the answer to this question, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel by clicking the bell so that you don't miss any of our weekly videos. If you would like to help improve the quality of our content, please check us out on Patreon. We would like to say a big thank you to all of those who show their support. Scientist Lynn Collison, who has worked on other planetary missions, noted that the detection of the signal recalled another episode of his life. It was pretty much the same kind of signal recorded by the Galileo probe when it skimmed through the ionosphere of Jupiter's moons, a layer of atmosphere also seen on Earth and Mars, where solar radiation ionizes the atoms, resulting in a charged plasma that produces low-frequency radio emission. I know what you're thinking. Okay, we detected a radio signal from Venus, but why is it so important for us? Well, the answer is that once the researchers realized what the signal was, they were able to use it to calculate the density of the Venusian ionosphere and compare it to the last direct measurements taken way back in 1992. Fascinatingly, the ionosphere was an order of magnitude thinner in the new measurements than it was in 1992. The team believes that this has something to do with solar cycles. The solar cycle, or solar magnetic activity cycle, is a nearly periodic 11-year change in the sun's activity measured in terms of variations in the number of observed sunspots on the solar surface. Sunspots have been observed since the early 17th century, and the sunspot time series is the longest continuously observed and recorded time series of any natural phenomena. The magnetic field of the Sun flips during each solar cycle, with the flip occurring when the sunspot cycle is near its maximum. Levels of solar radiation and ejection of solar material, the number and size of sunspots, solar flares, and coronal loops all exhibit a synchronized fluctuation from active to quiet to active again, with a period of 11 years. This cycle has been observed for centuries by changes in the Sun's appearance and by terrestrial phenomena such as auroras. Solar activity, driven both by the sunspot cycle and transient aperiodic processes, govern the environment of the solar system planets by creating space weather and impact space and ground-based technologies, as well as the Earth's atmosphere and also possibly climate fluctuations on scales of centuries and longer. Understanding and predicting the sunspot cycle remains one of the grand challenges in astrophysics, with major ramifications for space science and the understanding of magnetohydrodynamic phenomena elsewhere in the universe. Skywave modes of radio communication operate by bending radio waves through the ionosphere. During the peaks of the solar cycle, the ionosphere becomes increasingly ionized by solar photons and cosmic rays. This affects the propagation of the radio waves in complex ways that can either facilitate or hinder communications. Forecasting of skywave modes is of considerable interest to commercial, marine, and aircraft communications, amateur radio operators, and shortwave broadcasters. These users occupy frequencies within the high-frequency or HF radio spectrum that is most affected by these solar and ionospheric variances. Changes in solar output affect the maximum usable frequency, a limit on the highest frequency used for communications. Anyway, measurements of Venus from Earth suggested that Venus's ionosphere was changing in sync with the solar cycles, growing thicker at solar maximum and thinner at solar minimum. But without direct measurements, it was difficult to confirm. So they went back to the 1992 measurements. In 1992, the Sun was close to solar maximum. The 2020 measurement was close to the solar minimum, and they were both consistent with Earth-based measurements. When multiple missions are confronted confirming the same result one after the other, that gives you a lot of confidence that thinning is real. This is what astronomer Robin Ramstad of the University of Colorado says. The question now is, how can the solar cycle affect in such fascinating ways the ionosphere of Venus? Scientists say they have two leading theories. The first is that the upper boundary of the ionosphere could be compressed to a lower altitude during solar minimum. This would prevent atoms ionized on the day side from flowing to the night side, resulting in a thinner night side ionosphere. Unfortunately, neither of these mechanisms could be ruled out by the Parker data, but the team hopes that future missions and observations might be able to clarify what's going on in their turn. Here's where all the importance of this discovery lies. A new and better understanding of the Venusian ionosphere could help us to gain a better understanding of why Venus is the way it is compared to our Earth. And since a lot of planets share common ionosphere features, this could also bring new knowledge in the field of exoplanets. What are your thoughts about this video? Let us know in the comments below, and don't forget to share. Science needs you, and you need science.